Hello. Yeah, absolutely. Well, welcome back, folks. Looks like we can get started. So we're working about halfway through the notes in section 4.3, but the bigger announcement is just a redo of what we said on Tuesday's class. Our second exam is going to be next Tuesday. It'll be specifically across those 5 sections that we see there. And these are the same exact kind of materials we saw in exam 1, just now repurposed for exam 2. This will be the actual sheet that you'll have included on your exam 2. And these are just more problems to take a look into for extra practice. Very first thing you should do to be fully prepared for the exam is definitely get caught up on the homework if you haven't. If you've already done with the homework, take a look in the feedback, make sure you understand how the problem should go if you missed any points here or there. And don't hesitate to ask questions about that in office hours or email, and I'll be happy to help out. Well, that's pretty much all I have to say about the exam. It's just going to be kind of a redo of what we did on exam 1. One thing to keep in mind for the in-person section, it'll just be in this classroom. At the same time, we have ordinary lecture. For the online section, we won't have class. It'll just be the exam. Don't forget to schedule your exam with the instructions I sent through Canvas. And if you're having any trouble finding those instructions, don't hesitate to write me a message, either in Canvas or Gmail, and I'll get back to you as soon as possible. Well, another thing to keep in mind for the in-person section is that there is a weird kind of fairness issue because we mentioned this on exam 1. Let's just reiterate it because it's been a while. For the online section, the exam is open to be scheduled between the dates of the 9th through the 12th. And for the in-person section, I'm only giving the exam on one day, the 10th. But I'm extending that same opportunity for everyone, whether you're in the in-person section or the online section. For the in-person people, if you prefer to test a day early, or if the 11th or the 12th just works out better, say maybe your other things are happening with other classes, I can send an exam to the Idaho Falls Testing Center, just so that there's fairness across both sections. Well, that's pretty much it for the announcements. Any questions at all, folks, before we start today? Okay, well, we're looking into proofs and proof techniques. In my opinion, it's a tough section at first, but once you get some really good practice on it, it becomes a pretty fun section. Really, all we're doing is everything we did in chapter 3 now applied to making really, really strong arguments of mathematical facts. And here's the one that we left off on. This is a pretty tricky statement, and we're going to prove it not directly. A direct proof on this one looks like it's going to be nightmarish. It might require a lot of ingenuity, maybe additional mathematical background to get through. Instead, what we did was we took this whole statement and we kind of just untangled it. If we take an implication, which is what example 5 statement is, rewrite it as a contrapositive, it just became the statement if x is a rational number and y is a rational number, then x divided by y is rational as well. And I did have one thing when I was looking at this morning that I'd probably want to just really emphasize when I said this part right here. We know x and y are real numbers, but y not being 0, I think it's a good idea to just restate when we're down here, just to be extra precise and not accidentally divide by 0 anywhere in the proof. That's definitely going to invalidate it. So let me just rewrite this part. If x is a rational number and y is a rational number, but we'll set minus the element 0. So now we're saying y is not 0 and it's rational. So just the kind of rundown on how we got this contrapositive statement. We took an ordinary P implies Q statement, but we rewrote it as not Q implies not P. So this whole statement here in green is not Q. And we're not saying the rational numbers, we mean just the letter Q, as in P implies Q. And that's kind of a conflict. Let's maybe change that to lowercase so we don't get mixed up with rational numbers versus a proposition Q. So lowercase p implies lowercase q. Now we're changing it to the contrapositive. So this entire statement here is not Q, and this entire statement is not P. We also had to use De Morgan's laws, so that's why we see it and represented. We negated this. Negation of X is irrational, means it's rational. We flipped the or into an and we made YB rational as well, but set minus 0 to include that condition. Well, that's the entire contrapositive. Any questions at all about it so far? Okay, now that we know the easier statement we're proving, which is logically equivalent to this one, the moment this is proven, we've proven the original statement as well by this proof method. Let's also quantify what we're dealing with here. That'll give us a better lay of the landscape when we go to prove this entirely. We have two variables, so this will be nested quantifiers, and really two different sets, the full set of rationals and the set of rational numbers set minus the 0. So we'll say, to start out, for all x in Q, we're saying it's a fraction, essentially, a rational number. For all y in Q, so also a fraction, but not 0, we want to show this statement, x divided by y, is in Q. So that's our full statement we want to prove, same as the one above, but now just a different view. We're looking at it from the point of view of quantifiers. When we're proving the contrapositive, really all we're doing now is a direct proof, much like examples 1 and 2 of this statement, the one that got turned around. So now that we've got it quantified, we can launch into the proof. And as far as the proof goes, whether we're looking at the quantified statement or the contrapositive right above, we're essentially going to start the same way. We have to say exactly what the variable x and variable y is. So every variable we put down on paper, when we go to write down the proof, has to be defined. So we begin by saying proof by contrapositive assume x is in Q, so it's a rational number or a fraction, you could say, and y is in Q, but non-zero. So we've defined our variables. Next thing we'll do is go to section 2.2. The moment we said we have two elements in Q, one of them having to be Q minus 0, we get to write those elements in this form. It means we can pick an integer p in z, another integer q in z plus, so that we're avoiding divide by 0, to rewrite those elements in this form. Again, we're just looking at them as a fraction now. So using this information here, all the way back from section 2.2, we can say next, then for x, there's going to exist, I'll just go a, b, c, d. There's going to exist an element a in the set of integers. And there will exist another element, b, in the set of, let's match up the notation that we saw here, where we are, there we are. We're saying positive integers, and that's a fine way to write a fraction, because if it had to be negative, the numerator could be the negative element. So I'll use the same notation. We're just avoiding dividing by 0 by saying it this way. B is in z plus, such that this element x right here is now just a divided by b. So we defined the variable x. When we wrote it as a fraction, at the same time, we have to quantify all extraneous variables involved in that. So this part's required in our proof writing as well. We have to declare every single variable that we write down. We're going to do it again for y, but any questions to that step there? Okay, so redoing this for y now, we can say there exists. I'll use C and D for the next ones. Now, y can't be 0, but it could be positive or negative. So we can write it this way. Let's say an element A in the set of integers z, but cannot be zero, so we're going to set minus 0 to eliminate the possibility of the fraction y itself being 0. Then there's going to exist some other element. Oh, let me start over. I wanted to have c there, getting distracted on the variables. So let's start with an element c, that's going to be the numerator for y. Then an element d, that'll be the denominator. This will be in z plus again, so that we don't divide by 0, such that y is going to be equal to c divided by d. So we have an x, we have an y, everything's been completely initialized, and we're really just on this part. We assumed that this is true, and it's a lot of writing when you assume something like that. The reason we had to write all this out is, if we're trying to show the conclusion that xy is a rational number, we're really just looking at that set again. We have to have something algebraically to get that form. And these are the two algebraic pieces we can use. We're just going to take x divided by y, see what this resolves as after we declared the variables, and show it fits that format right there, that we are now included still inside the set Q. So now we're on this phase, x divided by y. Next, x divided by y is going to be a over b divided by c over d, which is a over b times d over c. Of course, we could have sped through the arithmetic, but let's keep on going. A times d divided by b times c. That looks pretty good. It looks like a fraction, right? But just because we put it on paper doesn't automatically mean it's a fraction. We have to be really careful here. What could go wrong is we divide by 0 on paper. If we declared the variables incorrectly, and there's a possibility of 0 in that denominator, the whole proof is just ruined at that step, right where the red dot is. So recall when we put this form, the denominator, whether we call it q or b times c, has to be non-negative. That way we're avoiding divide by 0. So we look at where b came from. B was a non-negative integer. We have to also look at where c came from. Well, c, it looks like it can be negative, but the critical thing is it excludes the 0. So if there was a negative, we can use arithmetic to push the negative up into the numerator and still be okay on this spot right here. So a times d, a could potentially be 0, but that's okay. X divided by y could have been 0 if x itself was 0. What we have here is a bona fide fraction because we avoided divided by 0 whatsoever. And so let's say here for our conclusion, this shows x divided by y. Let me keep that same color to match up with the target right here, trying to get to that conclusion. This shows x divided by y is in Q because AD is absolutely an integer. When we take A times D, they started as integers here to here. That ends up as an integer. And the big part is B times C has no possibility of being 0. So we're looking at a bona fide fraction altogether. And that's the conclusion we want to show. We start with two rational numbers, and the second one is non-zero. Divide in this way, where that's the non-zero one, it's still a rational number. The fact that we proved here is tricky because there's lots of moving parts. There was a total 1, 2, 3, 4, 5, 6 different variables that we were tracking all at once at the same time. 4 of them right here that we had to analyze again, particularly just the 2 in the denominator. But once we got to that statement there, the proof is over. Any questions or comments at all, folks, running through this one? Okay, well, this is where our logic was, again, really massively helpful. This as a mathematical statement really isn't that big of a deal, really, but it's amazing that this statement here where the red dot is completely logically equivalent to that one. And even though it's a believable statement still, this one looks really, really hard to prove directly. I don't even know how we would start that. I would absolutely want to look at it from the point of view of the contrapositive. But let's say one more thing just for the sake of reiterating the comments that we mentioned before in homework writing. There's a lot of stuff that we have to do when we run through a problem like this. So let's say here, additional comments for homework and exams, although this is going to be an exam 3 and then a final exam type of content. Here's the entire statement once again. And these statements right here are duplicated on the homework problems as well, just for emphasis. For homework problems, we have to hit all 3 bullets right here. And it can be tedious. Sometimes it feels like you're really saying a lot to just run through a really small set of steps. But think along these terms. In mathematics, we have to be extremely literal. We have to say what we mean, and we absolutely have to mean what we say. And computer science is no different. Imagine what you're really writing, just for the sake of an analogy, is just some kind of program. Any kind of program you write will not compile. It's absolutely not going to run unless you initialize, declare the data type of every single variable that you write down on paper. So when you write down a proof, say for homework or an exam, imagine you're the compiler. You're going to read that line by line by line, and the moment you see a variable x, but it's never qualified what the data type is, how it was constructed, the whole program is going to terminate right there. We're doing essentially the same thing when we say quantify all variables. We're being extremely literal. We can't just take an x on face value and know what it is. If you say deleted this whole entire part, and you told me x is a over b, y is c over d, that's not good enough either. Even if you declared that x and y are integers and the second one's rationals, and the second one is a non-zero rational number, you can't write down this either. This is meaningless until you say exactly what A and B are and C and D are, where they come from, what type of data it is. They are integers, then non-negative integers, non-zero integers, and then non-negative integers for all those variables. So we have to say this, and all of this right here to target that part in the proof writing. And we could lose a lot of credit if we're doing this, say, as a homework problem and even as an exam problem. But if on your first attempt on this, you did lose a lot of credit, I'm going to give people an opportunity to rewrite this homework set. This one takes a while to grade. It's going to take a while to do, but being really careful, getting another opportunity to run through these kind of steps, making sure we hit everything, will get us well prepared for the exam. Any questions at all, folks, about that first bullet, quantifying all variables? Okay, this part right here, that's the part that's not as tricky, I'd say. Show all logical algebraic steps. By logical step, we meant write down the contrapositive, and we absolutely did that. Algebraic steps were pretty much right here. We were showing if and then. And so another logical step was ending the proof because we got to the conclusion, and then we were essentially done at that spot. I guess it kind of goes together with clearly stating the conclusion as well. For that bullet right there, we had to land right here to complete the entire proof. And so we had to say this part. If we left it off and we just said this much and just stopped, the proof isn't complete. We have to go beyond and say, what does that mean? That you have xy is AD divided by BC. You have to say it in ordinary words. This shows xy is in the set of rationals, which is what we were trying to do in the very first place, land on that conclusion there. So that's another just view of the requirements for the homework, as well as when they're on exams as well. Any last questions or thoughts, folks, before we try out a whole different kind of proof? Okay, well, let's turn this over to another proof technique. We're going to use contrapositives again in these notes, so it wasn't our first look at it. Another really tricky type of thing to prove is any statement that has an if and only if baked into it. And there's plenty of those in mathematics. Some of those theorems that involve an if and only if, or many, many logically equivalent statements, are some of the nicest theorems that you encounter in mathematics. But proving them is a bit of a chore, like we can kind of see here by the statement. It says, just as a warm-up before we prove this if and only if statement down below, we're going to take another look into the biconditional and prove a logical equivalence. And this is also a good reminder that when we were in chapter 3 and we proved tautologies, statements are as tautologies, or we proved two different propositions are logically equivalent, it's really the same kind of proof we were doing. We were just purely constrained in logic. And here, example 6 is just an application to that logic. But this is going to be an honest proof, just like everything we've been doing in these notes. And here's how it's going to go. Good warm-up problem. So this is essentially a good exam 2 review problem on its own right here. On exam 2, we're going to have to write down some truth tables. Let me try to do that a little bit better. So I want several rows. That should do it for us. Then the left side and the right side of the logical equivalence only involves two propositions. So we only need this many rows and propositions P and Q to start. Then we can go true, true, false, false for P, true, false for Q. And the first thing I would do to verify this is just look into the if and only if. Quick reminder how this one goes. Let's go to section 3.2. The if and only if statement is saying P if and only if Q is true only in the cases both P and Q have identical truth assignments. That's why we got true on this row and on the bottom row, even though it was false, false, and false elsewhere. If there's a mismatch on the logical assignments, the if and only if comes out as false. So that's just our refresher on that. Let's put in P if and only if Q. Let me try again. P if and only if Q. This one will go true. Every row that has a mismatch, we go false, false. But these are the same truth assignments, so true here as well. Now, this one we can do, all at once if you're really, really good at that. But for me, I would do it in 3 pieces. I want to do the P implies Q, Q implies P, and then the conjunction, the and statement in the middle. So P implies Q, refresher on that one is it's only false one possible way. That's when P is true and Q comes out as false. So that's the only false in this truth table, true elsewhere. Then same idea with Q implies P, except we're going backwards, so we have to be really mindful of the direction. Q implies P, let's look for the false. False will only happen if you're already at a true, but you go left from Q into P and land on a false. That happens right here on this row. It goes from true into a false. So we only get a false here, and everything else is true, either ordinary truth or, say, a vacuous truth on these two. Or hang on. Yeah, vacuous truth, and an ordinary truth. Got a little mixed up on those assignments. So true, true, and true. So those are the 2 individual pieces. Now we put it together. P implies Q, and Q implies P. And by the way, when we were doing these as exam questions, I'll make liberal use of parentheses. So it's really very clear how the logical order of operations will work on the problems. It won't be left open to interpretation. I'll make sure to insert as many parentheses as needed for clarity, like we see here on this one. But now we're looking at the conjunction, and this one is going to be true only when both this one and this one, the left and the right side, are true as well. So we get true on this row. The moment a false occurs, the conjunction statement comes out as false. So false because of this one right here. And then we have true and true again, so we get true on this statement. So taking a step back, on P if and only if Q, we had true, true, false, or excuse me, true, false, false, true, said those weird. And then on the right, P implies Q and Q implies P, we have true, false, false, true. That's what logical equivalence is really all about. Logical equivalence tells us the truth assignments are exactly the same as we go down every single row. So a P if and only if Q, we now know is logically equivalent to really just two implications. P implies Q and Q implies P. But this essentially informs us on what the proof method has to be. Before we take a look into that, any questions at all, folks, on just verifying the equivalence? Okay, here's the takeaway for what we have to do now. If you detect an if and only if in any mathematical statement whatsoever, to prove that, you could potentially write down a sequence of statements that are all if and only if statements. And there's some clever proofs that work out really nicely like that, but it's not always easy to make that happen. And that's going to be really hard on this one. To start at 11x minus 7 is even, and every statement I have to make has to work forwards and backwards. There has to be a sequence of if and only if statements, and somehow land on x is odd. In my opinion, that sounds really, really challenging. However, you can use the mathematical idea of divide and conquer. You can use a logical equivalence and just prove two statements. And if and only if can be broken down into two direct proofs. Your first direct proof will be you must show P implies Q, much like we did on examples 1, 2. In the very last example, although it was a contrapositive, not Q implies not P. So that's the forward direction. You're going left to right, showing P implies Q. But to show the biconditional is really true, you have to back it up. You have to go to Q implies P as well. The logic has to reverse, in other words. So step 2, you must also prove Q implies P as well. So that's the process for proving an if and only if. It's not the only way to do it, but it's the overwhelmingly more typical way you'll see these proofs go. And even if there's a short proof trying to do a sequence of if and only if statements, starting from P ending at Q, oftentimes when people write down proofs, they still break it down because it's easier to see it happen in one direction and then see how it reverses at the same time. Sometimes these proofs are just more informative to actually read rather than trying to skip the logical equivalence and go directly. So that's the setup so far for any biconditional statement. Now we're going to give this a try. But any questions or comments at the moment? Okay, we're going to start off like we have on a lot of problems. We're going to quantify the statement first. It says we have an arbitrary integer x. We're told then, if that is the case, then 11x minus 7 is even if and only if x is odd. So to quantify it, you could say for all x in z, looks like just one quantifier this time. I'm going to write it out this way. 11x minus 7 is even. Here's the biconditional, if and only if x is odd. So that's our statement to prove. And thinking in terms of this is really just two direct proofs, we'll think of the left-hand side as being the statement P, the right-hand side as being the statement Q. Here's how the proof is going to go. First, we will show 11x minus 7 is even implies x is odd. Now, if red flags have come up already, then good on you. One thing I haven't done yet is I haven't said what x is in the very first place, so I haven't quantified it yet. So that's going to be my next additional step once I start to try to prove this. But I want to show how this could actually go wrong. We've looked at a lot of proofs that just kind of flowed. They got from a start to an end and no hiccups ever occurred. But this statement right here, the first direction P implies Q from the biconditional, is tricky. So let's write down this on paper just to show what can go wrong. So let's say we begin by saying, let x be an integer z. So now we have declared what that variable is. It's been quantified. It's any arbitrary integer. And if we're going to do this as a direct proof, just as it reads on paper, we would probably make this assumption. Assume 11x minus 7 is even. And that's a natural assumption to make, right? That's how our implications have gone pretty much each and every time. Then we'll look up some specific mathematical facts relative to that statement. 11x minus 7 is even means, here's the essence of evenness. There's now an existence of an integer k such that in place of n is 11x minus 7 is double that integer. So if we just keep following our nose on this and use that next definition, we would say this on paper. Then there exists some integer k, exists k and z such that 11x minus 7, the moment you say it's even, it means it's double some other integer. So we say it's equal to 2k. Now, our goal is to show x is odd, right? That means we're trying to get this structure, x equals 2k plus 1. The moment we get something like that, and it doesn't matter how weird that integer k is, it just has to be an integer, our work is done right at that step. But this is all we have, just one equation. And if we kept going forward on that, we could say then 11x is 2k plus 7. Then take another algebraic step. We can divide by 11. X is 2 11ths times k plus 7 11ths. We're in trouble right at that step. Here, the proof is essentially stuck. We're trying to make it look like that to 2k plus 1, but there's no factoring you can do here to get there. If we try to factor out the 11ths, we don't have the 2 whatsoever. If we factor out a 2, well, then we have 1 over 21 times k plus 7 over, not 21, but 22. Or hang on, if we factored out 2, let's just do that on paper so it looks right. We factored out a 2 to just try and force this structure that we see down below. We would get an 11th times k plus 7 22nds. But that's not helpful. We don't have the plus 1. And even if we try to rig it so a plus 1 shows up, we're still in bad shape because this right here is not an integer necessarily. Maybe for some values of k, it might work out when we add the fractions that it comes out as integer. But k is arbitrary. We can't pick a specific value. We are doomed right at this step. It's not guaranteed to be an integer any longer. That means this direction failed using this approach. Let's put this on paper. Not an integer. And so the proof method failed. We didn't do anything wrong. It's just, it doesn't work in this direction. The algebra is too messy, and we can never guarantee that type of factorization, 2k plus 1, where k is a guaranteed integer any longer. So that's kind of annoying. Sometimes these directions just don't go in the way you would like them to. But we have another trick in our toolkit that's going to resolve this. But any questions at all, folks, on this misadventure? Okay, it's just as important to see when things don't work out, because this can absolutely happen when we're doing our problems in the homework. It could happen on exams. And if you get in this tricky algebraic situation where things just aren't working out, here's what we can do to resolve it. Take this statement. It's inconvenient as written. And if that's inconvenient, turn it around. We're going to consider the contrapositive instead. We will prove it's contrapositive, which means we should write that down immediately because that's what we're going to prove. Recall how the contrapositive goes. Let's put that on paper as well. If we have a P implies Q, then the contrapositive, I'll say this way, has contrapositive, or logically equivalent to the contrapositive is another way you could say it, to not Q implies not P. So that's what we're going to go for. Here's the Q statement, the conclusion. Negate that, and all you're saying is X is even. We want that to imply, so that's this part of the contrapositive, the negation of the original hypothesis. That's this part right here, but negated, it's just saying 11x minus 7 is odd. 11x minus 7 is odd. So that's the statement we're actually going to prove. And when we go through the proof, we'll declare all variables, we'll quantify every variable that comes up, and try to land on 11x minus 7 is odd. Essentially the same direction that or same kind of statements we proved here, but if you have something like 11x minus 7 proved as even, these type of directions often get stuck. If you prove just x is even, then algebraically things just have a way of working out. It's kind of mysterious in a certain sense. So let's give this a try now. We're ready to begin in earnest. And let's say, to give a direct proof, we assume this part is true. Let's just say that with ordinary words. Assume x is even. This means there will exist an integer k, exists k and z, such that x is twice that integer. X is 2k. Let's just pull for reference. So here's the definition of even right above, and that's essentially all we said, placing x in position of n. Now that we have this part right here, we consider 11x minus 7 trying to land on odd, so trying to get to that structure we see below. We'll say next, trying to hit that statement. Then x minus 7 becomes 11 times 2k by substitution minus 7. So this then turns into 22k minus 7. Well, doesn't look that super convenient, but let's put this on paper. If we really twist its arm, we can get this in the right form to match up with this, the statement for odd. So first thing I need to make that work is I need a +1 inside there. I can't just put +1 here without balancing the equation, so we can rewrite this as 22k minus 8 plus 1. That does the job because this combines like terms to back to the -7. Once we have the +1, now we can factor out 2 from these terms right here. It turns into 2 times 11k minus 4 plus 1. And now that's really good because what we found is an integer. 11k minus 4 is a guaranteed integer. This was not. That depends on k. But no problems here. If you picked an integer, multiplied it by 11, reduced by 4, we have a nice closure property of those operations. We're still an integer at that step. So we can now conclude this shows 11x minus 7 is odd because 11k minus 4 is an integer. It's in the set Z, in other words. So this whole statement right here exists an integer is what we were saying for this part. The integer had to go right there where k is. There it is, right in that spot. But you also had to double it and add 1. The moment you did all of those things, you've got an odd expression, an odd integer in its entirety. So it took a lot of different kinds of algebra from compared to the other examples, but the conclusion is absolutely odd. The moment we got double an integer, add 1. Well, that was one direction. That was the going from left to right. Now we have to reverse the logic and show that if we start with an odd integer, can we then change the direction and conclude 11x minus 7 is then even? So we just went that way. In other words, we want to go that way next. And if we can, we've proven a biconditional. Well, this is a good moment to catch our breath. These proofs are fun in a certain sense, but they're also annoying in a certain sense because it's two proofs really duct taped together by the if and only if statement. So now we need to redo this going right to left. Any questions first, folks, in the first direction? Okay, so far, looking at what we said above, that part's done. Now we're changing the order. This was the Q. We're going right to left, landing here. We said first we'll show something, and these are really good organizing statements. You don't have to put it on paper, but it's good to alert the reader how you're flowing through the proof. And if no one else you're trying to alert to, you're trying to convince yourself that you're hitting all those steps. And even though it doesn't seem like a big statement to say, just saying yourself in ordinary words in your head and then writing it down kind of primes your subconscious on what you're about to do next. So let's take that step again and say, next, the proof is complete once we show x is odd implies 11x minus 7 is even. So one more direct proof to show, and this one's not so bad. We didn't need a contrapositive this time. On our first attempt, or not our first attempt, our first direction, left to right, we proved the contrapositive to get that statement proved down. Here, we don't need such tricks, so we can immediately now just say, assume this part. Assume x is odd. This means x, let me start off first by quantifying the k. This means there exists an integer k, exists k in z, such that x equals 2k plus 1. Much like we had to work really hard here to show odd, this time we just declare what the variable k is and write x in that form. If it's odd, there is absolutely some integer k that will solve that equation there for x. We have to land on 11x minus 7 being even, but that's just like we did on the contrapositive proof over here. It's just a bit of algebra. We'll say, then 11x minus 7 becomes equal to 11 times 2k plus 1, then minus 7. So now let's do the algebraic steps. That's 22k plus 11 minus 7. Combining like terms gives us 22k plus 4. And that's not so bad. We can factor out 2 from both of these terms to get 2 times 11k plus 2. Let's take a look at the essence of evenness once again. Even means you found an integer, you doubled it, and it's equal to the thing you're considering. N in this problem is 11x minus 7. We have our times 2, here it is, factored out. And the integer k is this, 11k plus 2. That's absolutely an integer. So our work is complete at this step. We just have to say it. This shows 11x minus 7 is even because 11k plus 2 is in the set z, or you could say the same language is an integer if you prefer. And that was the last direction. We proved this direction here. So now the proof is complete right at that step. This completes the proof. So that's how an if and only if statement flows. Each and every time you encounter one of those, this is a really great strategy. There's, again, other strategies. We could have started with some statement, maybe starting on X, only making if and only if reversible statements all along the way, and try and land at this side right here. But again, those are really tricky proofs to kind of get through, because the moment you write down something that's not reversible logically, the whole proof just falls flat on its face. So the divide and conquer method, show one side, then reverse it, show you can go that way as a direct proof, is a great technique for any kind of if and only if statement you ever encounter. Well, we did, folks. That's the biconditional. Any questions on getting through this kind of proof? Okay, we have really one more proof technique to look into, really two more. We're going to also show how to disprove something when we have, say, a universal quantifier. But the next major proof technique before that one is proof by contradiction. This one is kind of fun in a way. It's a challenge in logic on how exactly these go. But once you get through the logical kind of hoops you have to jump through, it's a pretty fun proof technique. It's wildly applicable, which is impressive as well. We can prove by contradiction that something like this, square root of 2 is an irrational number. That's kind of a fun and strange proof technique. So here's how it goes. In a proof by contradiction, we assume the negation of phi. Phi represents the statement that we're trying to prove, like, say, square root of 2 is irrational. If we're trying to show the square root of 2 is irrational, proof by contradiction says, we'll assume that's not the case. Assume square root of 2 is a rational number, that you can write it down as being equal to some fraction. You assume the negation of phi, but if that's a true statement and you've negated it, you can take some algebraic logical steps to derive a contradiction. Now, if you've derived a contradiction, that would tell us that the negation of phi was false. We landed on something that broke math or broke logic. The moment we assume the negation is true, we end up on a contradiction. Then the negation of phi must have been false. Then we can use another idea. This goes all the way back to 3.3. Forget exactly what the name was. Law of the excluded middle. There's only two things that can happen. Either the original proposition phi is true, or the negation is true. So if we negate phi and get a contradiction, then we can say, well then, that would have meant the original statement phi was actually true. And that's the whole method of proof by contradiction. Any questions about it so far? Just the logic of how the method goes? Okay, let's put down something on paper just to convey all the words that we just said. So once you derive a contradiction, once you run into a statement along the lines of 5 = 2, any kind of contradiction like that, something that just doesn't work out mathematically, algebraically, or logically, we can say the assumption that not phi, we say assume the negation of phi, that means we're assuming not phi is true, is what led to the contradiction. Therefore, and that was supposed to be phi. I don't know how Q got in there. Let me match it up with the definitions variable phi. The assumption not phi is true is what leads to the contradiction. Therefore, phi must, and that's always a strong word, but it must be true. And again, that is just our first real direct application of the law of the excluded middle. If this hit a contradiction, then the original thing, we called it phi up here, must absolutely be true in that case. Well, that's the whole method of proof by contradiction. And people in philosophy like to call it this, reductio ad absurdum, which is kind of a fun way to call it. It's Latin for reduction to absurdity. And that's exactly what you're doing in proof by contradiction. Assume the negation of phi and keep on arguing until you hit the wall, the absurd statement, like 2 = 5, something that is absolutely false. Then you undo the negation of phi, you say the original statement must have been true. That's exactly what we're going to do in example 7. If x is rational and y is irrational, we will show x plus y is irrational. But that's actually a hard statement to prove directly. The reason for that is to do a proof on this as a direct proof, let's go back to our sets of numbers, we can do something algebraically with the statement x is rational. We just write it as p over q. But our statement y is irrational gives us nothing algebraically to work with. So we can't just say, trust us, x plus y has to be irrational. We need to show it. And actually showing those steps on paper is really, really hard as a direct proof. Again, I'm not sure how I would do this one. I'm not sure if that's something I would even try to do. I would go for the proof by contradiction on this one, absolutely. But another thing that's problematic with it is this is an if-then statement. So it's a P implies Q. That's taking the role of phi, an entire implication altogether. We have to assume the negation of the implication. And we got this. We've proved this one directly. This was way back in section 3.3, once again. 3.3 had a lot of gems that we're using, finally. And way down below, that's too far. Way too far. I think we're there. Here we are. Right here is where we negated the implication. We showed that negation of P implies Q is absolutely logically equivalent to P and not Q. Notice the truth assignments are, hang on, yeah, negation, I'm looking at the wrong column there. The truth assignments from the negation of the implication and the statement P and not Q are exactly the same. So let's put this on the notes just as a refresher. So through that logical equivalence there, it tells us how to negate the statement in example 7. If x is rational and y is rational, this whole part right here is the proposition P. in the P implies Q implication structure. This part, x plus y is irrational, is the proposition Q. So we're going to negate it, which means we're just going to say, we're going to assume P is Q, or excuse me, we're going to assume P is true. We just assume that whole part right there. Then we also assume the negation of Q is also true. We're going to assume X is rational, Y is rational, and it's a literal and logically, X plus Y, remember we're negating it, is rational as well. So that's going to be our proof technique on this one. The negation is if X, I'll say it's just using our set notation. If X is rational means X is in Q, and Y is irrational means, hang on, I made a mistake here. It's tempting to write down the if, but recall, when we negate the implication, it's no longer an implication any longer. So me putting in an if then makes no sense. We just have to say this part. If X is rational and Y is irrational, so Y is in the set I, that's our symbol for the irrational numbers. Ignore the then. It's just another and we tack on, coming from this and right here in the logical equivalence. And X plus Y is rational. When we negated that, we just say it's in the set of rational numbers. So this part right here is the negation of Q. So that's the statement we're going to prove on this one. Any questions at all, folks, on the negated statement? Okay, again, it's kind of cool to see how chapter 3 was really trying to work. Pretty much everything we were doing in chapter 3 has a really fast, direct analog to just ordinary statements like these, except for maybe stuff like this would be harder for me to come up with a problem. That one was more just for the sake of studying truth table for its own sake. So now to prove this statement, well, we're going to use proof by contradiction. So here's how it's going to go. We want to prove the original statement here, so we'll say proof by contradiction, just to indicate here's the method we're using. Assume X is a rational number and Y is a rational number. Assume also that X plus Y is a rational number as well. So we made all the assumptions coming out of the negation using the logical equivalence right here. And again, if you do any kind of proof by contradiction on an implication, that's how it always goes. You assume both the hypothesis and the conclusion at the same exact time. It's kind of amazing in a certain sense. This gives us a lot of tools all of a sudden. Proving this directly, we're missing a tool right here that Y is irrational, and it's hard to know how to even start this. But now we've made an additional assumption. That's not true. It's also rational. So let's show how all this goes. Just a refresher, we're now back to this set right here for both X, or hang on, I made a mistake. Y is irrational, right? So I assumed X is rational. I need to say Y is in the set of irrational numbers. So that was a mistake right there. Let me fix that. Y is in, let's make that pop I, the irrational numbers. So back to our set. Sorry for that distraction there. That's one thing that was kind of what's going to make the proof arrive at a contradiction. Now for both X and X plus Y, we're just going to write it in this form. They're just fractions. But like we discussed before, we have to declare the variables. So let's start with this part. Then X and Q implies the existence of A in Z, the existence of another integer, B in Z plus, so non-negative, such that X equals A over B. So we've got one fraction down, and then we just do it again over here. That's the other one we can write as a fraction. X plus Y is a rational number, implies, I'll go for C and D next. There exists C in Z. There exists an integer D, non-negative, so Z plus, such that X plus Y itself is equal to C divided by D. So all I've done is worked through this part here and this part for a three-part assumption we're making. Y is a rational number, so it's hard to know what to do with that. But notice it's right there in that second equation. Also, we have a new way to write X. So that one additional statement on X plus Y being a rational number gives us a full equation that we can work with and isolate Y on. Let's say next. Then X plus Y equals C over D will imply we're really focusing on Y being an irrational. We're also going to swap in that X there for A over B. A over B plus Y equals C over D. That equation now implies, new implication, I just isolate Y this time. We're isolating the irrational part. Y is going to be equal to C over D minus A over B. And we could take an extra step and add the fractions together if we really wanted to, but we know something nice about the rational numbers. It is closed under the operation of addition, subtraction, and multiplication, divisions where it could go wrong. So the moment we took two rational numbers, added them or subtracted them, and even multiplied them, that's an automatic rational numbers because C over D is rational. We said that on this step right here. And A over B is also rational because of the way those variables are quantified. So we have Y equals that, which is a rational number. So now we take a step back. Let's look through our assumptions. We assumed X was rational. We assumed the sum, X plus Y, is also rational. They're both fractions. But we also assumed Y is irrational. We are now in conflict. We have hit a direct contradiction. Y is irrational here, yet Y is equal to a rational number. That's absolutely impossible. A number can't be rational and irrational at the same exact time. This breaks mathematics. This is absolutely a contradiction. We'll say here, but Y is assumed to be irrational. That was the statement right up here. And so we have a contradiction. I think it's fun to always put an exclamation when you run into a contradiction like that. We wanted the contradiction, and again, that's weird. Usually we're doing everything we can to avoid any kind of logical contradiction, unless we're doing a proof by contradiction. We wanted that to happen. How did we get the contradiction? Well, it happened the moment that we said X plus Y is a rational number. That was the whole cause to our contradiction. This contradiction emerged from the assumption that maybe it's better to just take a step backwards. It absolutely emerged from that statement there, but it was also just because we negated this statement. It allowed us to assume that. So this contradiction, it really emerged from the assumption that if X is rational and let me fix my spelling, and Y is irrational, then X plus Y is irrational. What do we do with that statement? We negated it, and then we assumed the negation was true. So I'll say here briefly, the contradiction emerged from assuming that the original if-then statement is false. We assumed the falsity of that statement, hit a contradiction, and so our proof is over. We can now say, therefore, that statement must, this is the law of excluded middle once again, it must be true. There's no other way around it. If we assume that this is false and we contradict a statement saying Y is at the same exact time irrational, but also a rational number, a difference of two fractions, we hit a contradiction, and it was because we assumed the falsity of the original implication. It's therefore true. That there's nothing further we have to show on that. Just, again, kind of incredible when you think about it. We never really worked with it directly in any shape or form. We didn't consider it's contrapositive at all. We just said, what'll happen if it's false? We break math right here, therefore it has to be true. And we'll show exactly how that goes with this one right here. Prove root 2 is irrational just by assuming it is not irrational. If it's rational, what goes wrong? What contradiction emerges? And the moment we hit it, we'll say, aha, we hit a contradiction, therefore root 2 is in fact an irrational number as well. Well, any questions at all, folks, on the run through with that first contradiction or proof by contradiction method?
How much of that belongs to Gray?
You could really paraphrase it well. I would say a paraphrase version might be Y equals C over D minus A over D is rational. However, Y is assumed to be irrational. Therefore, the original statement, and you can just say the original statement must be true. So you could paraphrase it way down to that, and that would be just fine as well. Other questions so far? Okay. Well, this one is, not too bad to get through, actually. What's really crazy about this one is we proved a pretty sizable chunk of this one already. It just didn't ever really seem like it. All the way at the top of the notes. These are getting long. All the way at the top of the notes. This is part of the proof. So we're going to cite example 1 when we prove that problem down below. So here's example 1. We'll just put it here to reference it. Now the trouble with the example 8 is this one's a little bit long. It's going to take me probably, I would say 15 minutes to discuss all the details. This is a big shortcut. The fact that we already proved something really major is going to help us out, but still a sizable chunk to get through on this one. Let's see, we've got some 5 minutes and some change. And this is a pretty important statement as well. This is another disproof by counterexample type of method where we're trying to negate for every type of statement. Actually, we kind of did these problems already. When we were in section 3.4 and section 3.5, we're trying to show that a universally quantified statement was false. You all were doing just that. You found that for all is false by exhibiting just one counterexample. So we'll take another look into this one as well. But I hate to rush through these problems. These are the least likely problems you would ever want to try to rush through. So we'll end class a little bit earlier this time, 5 minutes. We'll take a breather. This is kind of some intense stuff we're getting through. And we'll come back fresh to this section after we get through exam on Tuesday. So we'll be back to these notes on Thursday's class to finish it off, and then move into the proof by induction techniques. Well, sorry for cutting off class a little bit earlier this time, but I think we kind of earned a break. Any last questions or comments at all, folks, before we call today? Okay, and if you're super curious on how this one is going to go, pretty much it's just doing this sort of thing as well. Negate that statement. That means you're going to write square root 2 like this. But then the moment you do that, this stuff comes back on the table, evens versus odds, which means you can leverage this against it. And it's a pretty big challenge, I'd say, to get through. That's kind of a fun one to think about. So give it a try if you're curious, and we'll show all details on Thursday. But have a great weekend, folks. Take care, and I'll see you all next time. Thanks. Have a good one, George.
Professor, I have a question.
Yeah, sure.
I remember you saying that there's a submission date, but there's no like fake like policy on late submission. So I was wondering if that's still true or not.
Yeah, absolutely. That's going to be in effect for the entire semester. Really, the final date to turn everything in is effectively really just our day of the final exam on Tuesday of finals week. So yeah, if you got behind on any one of those sections, you're welcome to turn those in for full credit. I'll be happy to accept them.
Oh, okay, because I saw that you graded the 3.5 homework and I got a 0, so I was just
Oh,
wondering if that was
that,
still the case or not.
it is. That must have just been an error on my part. Let me take a look into that and put a quick note here.
That's okay. I was just wondering if I should write you an email or something or
This absolutely works too. That's a little bit more direct. So thanks for indicating that 3.5 homework. I'll check my files and get that re-uploaded, possibly sometime around Friday morning was when I'm going to be next with that
okay.
workstation.
Sounds good.
Again,
Thank
sorry
you
about
so
that.
much.
Make those
Oh no,
errors. I
that's all
appreciate you
good.
telling
Have a good
me.
day.
Thanks, you too.
Thank you.
See you later.